Yep, my name is Jason. I'm technical director. I've got some history of doing pass by noise back in the end of the 90s on motorcycles, but I joined the old LMS organization back in 2000 and been around here, LMS/Siemens, ever since. Really simple outline today, actually. So just a few things. We're going to talk about implications and solutions related to pass by testing, and then how we propose to increase pass by testing efficiency. And then after we talk really specifically about outdoor testing, the way we handle the actual acquisition and processing, I got a few slides that talks about advanced and predictive engineering, things that we can do more in like a pass by development sense than just a pure get my number and did I pass or fail in the regulation. With that though, let's jump in and just a couple of quick slides and implications. Some positioning here. I think there's no big amazing revelation to anybody. Of course, pass by noise regulation values or levels have been going down over time. This is actually a fairly old plot, I think, even, but we know they've been decreasing in the EU, especially, and with changes both in different markets, worldwide markets, US regulations also adapting, things like minimum noise coming about. But all these changes really mean that pass by testing itself has gotten a lot more complex. In fact, even the motorcycle testing I did had maybe a slightly more complicated standard where you had to reach a certain RPM within a certain range of the track and have RPM, so it was almost like a box you had to hit with the RPM curve coming up, whereas most cars where you come to a position, wide open throttle, accelerate through the trap. But of course, over time with these new regulations, there are things like you have to do ASEP testing of the number of gears, the power to mass ratio, the weight of the vehicle. All these things affect how the testing has to be run, and you need a lot more data to verify that you actually did do a good test. Throw in there too, like things like new minimum noise standards, which when I first heard of that, I'm like, oh, wow, you must just have your car make its noise and say it's good or bad. No, it's a lot more complicated than that, right? There's moving tests, stationary tests, different ways to average. So the job that we have to do as pass by noise engineers has gotten much more complicated over the last few years. And really, there's a couple ways that we will break down this topic. Like I said, we'll talk about efficient testing. That's both hardware and software, how we approach the actual data acquisition. But then also pass by noise engineering. And the difference here is that we want to be able to pick a standard, run the test, find out did we pass or fail, or what octave bands did we not pass, things of that nature. But many times you have to do actual development work to figure out how to make the vehicle quieter, or maybe increase third octave bands if it's a minimum noise test. All these things go into pass by noise engineering. So the old put a sound level meter there and just get a single number is not going to help you get your job done in most cases. And that's what we're talking about here with increasing testing efficiency. We review hardware for a moment because we have some very specialized hardware that we use for pass by noise testing specifically. Those of you on the call that are current Siemens customers are probably aware of this, the front end here. It's a SCADAS Mobile 05, portable system, AC/DC powered, can run on the battery for a while, has different slots to put in input modules for doing normal noise and vibration testing, field testing, things in the laboratory, etc. Well, we're leveraging the same hardware platform, of course, to do pass by noise testing, and it gives customers some value where they don't have to have a specialized investment just for pass by. They can use the same hardware they potentially already have to do that pass by noise testing. But then we have a couple specialized things that I want to point out here if I zoom in a little bit. So if we kind of come in closer on this picture, like I mentioned, there's, of course, the SCADAS 05, but if you're really up closely, you'll notice that one of the modules in the bottom left there is 2 slots wide. That one card takes up 2 slots in the frame. That's actually a telemetry module that has a mating pair in the small 1-slot frame that's over on the upper right-hand side of the slide. The top level is generally inputs to that card, and the bottom level is outputs. This telemetry allows us to handle what we'll call low-speed signals for things like engine speed, vehicle speed, a kickdown indicator like pedal position, the light barrier signals. All that data is quote unquote RF transmitted low speed. But if you want to have the possibility to put the measurement system inside the vehicle, we'll get to that in a moment, or you just want to simplify the setup and not run cables for the microphones, we have the possibility for the wireless microphones, which are shown right in the bottom middle of the photo. You can see the windscreens on them. Those need a high-speed telemetry system that allow the transmission of full audio bandwidth, 20 kilohertz bandwidth signals from the microphone position next to the track to the front end to make sure it's synchronous with all the other channels being measured, prove that the sound level at position is valid, etc. That's very important that we have the different types of telemetry there. And the wireless microphones are an option. People can say, nope, I've got an existing track with underground wires. I'm going to run a wire across the track and move it outside my measurement zone. That's all fine and valid, but they give a lot of flexibility sometimes to have the wireless microphones. In addition, you might notice the little blue box over here on the left. That actually is a V box from Race Logic. It's their simple velocity measurement unit. It's a GPS device that you just put the antenna on the roof or outside the car, plug in one single cable to our telemetry module. We both power that unit, measure the signal coming back, and we get that as an input to the system in pulses per meter in a calibrated position sense. One quick comment on the V-Box that's very different and really important for accuracy is that device does not measure the rate of change of position to calculate velocity. It actually uses the Doppler shift in satellite signals to compute the velocity. And there's white papers out there from Race Logic. You can see that it's actually a more accurate, robust way of doing that calculation. And then this device converts at 100 hertz that velocity into that pulse train that I mentioned, like the pulses per meter, to give us a speed indication, which we then use for position. Optionally, somebody could use radar, that's shown here in the picture. And then last, of course, we need some light barriers over on the far right to trigger both the stop and the end of the track to give us an absolute position measurement. All that being told, so this hardware setup gives me some possibilities for how I want to arrange it. And then this is a schematic of how it could be. This is actually showing a track-based setup where I put the main measurement system trackside, the computer is trackside, and it's hooked up to a weather station. I just skipped over the fact the weather station was there, that's measured as well. And then all that data is synchronized and telemetred from the vehicle there. But that scenario can actually be flipped around to give me a couple different ways that I can put the system together. So just in some high-level pictures here, to give you a graphic on that, if I do a track-based configuration like is shown in this upper left photo, like I mentioned, I'm putting both the measurement computer running the test lab software and the main measurement front end trackside. So this could have wired microphones or wireless, both would work in that scenario. I'm plugging in my light barriers, the weather station, etc. And the vehicle then is telemetering just things like engine speed, pedal position for wide open throttle indication from inside the vehicle trackside. But the exact same hardware I can actually flip around and use in a scenario where I put a vehicle-based configuration together, which allows me a couple different possibilities. First, I could put the actual person running the test in the car such that they can start and stop their measurement on the laptop. And it lets me add other measurement channels, which might be good, like I mentioned, for doing actual pass-by development work. Maybe you want to have a microphone in the engine compartment or near the intake, or measure some tire noise with a microphone outside, or something like that. There's a lot of possibilities that you get when you put the measurement system inside the vehicle. Or even CAN bus, for instance. We have some customers that use the CAN bus to get a throttle indication to know when they go to wide open throttle, or maybe the engine speed signal as well. And that's literally plugging in a cable and programming it one time, and then you can use that for those channels in the setup. Now you might say, well, but wait a minute, if the driver is actually running the test, that's probably not safe because the laptop's over on the side there. How are we going to handle that? How are customers allowing that? Well, we don't expect them to ever interact with the laptop while they're actually driving during the test. We accomplish that by actually having a wireless Android tablet application that shows up here, and you can see an example of putting it on the screen with a little suction cup, the feedback that the driver needs to run the test correctly. Now, if we look at this bottom left picture here, you see that there's actually a target speed of 48 kilometers an hour in this test that he's running. The arrows are both green because he's within the tolerance, probably 1 or 2 kph plus or minus. If he was to go too slow, and maybe it's indicating over here 45 kph, the arrow would be red on the top, meaning he needed to speed up. If I see it was too fast, it would say, nope, you need to slow down. So without having to focus on this, the driver can look at the colors of the arrows, know if he's within his speed range, know if he has to speed up or slow down. In addition, this big blue bar at the bottom actually is important as well. So in this case, he's running a test where I can tell immediately looking at the screen if the resolution is good enough on your side. The first orange bar coming from left to right is -10. The second one is 15.2. So that's position on the track when the driver is supposed to go to wide open throttle at the -10, and then throttle release at 15.2. Those values shown on that driver's aid come from the standard being run. He did not have to go program the tablet to say, okay, today in this car, my throttle off position, my kick off position is 15.2 versus 14.8. That comes in automatically to that driver's aid based on the standard and the vehicle and all the other inputs I'll talk about later that are put into the test lab software. In addition, when he hits the first light barrier, in this case at -50, a green bar will start progressing across. It'll literally move left to right and sweep over to that -10. And there's an audio tone that gives him a countdown, beep, beep, beep. And when it goes solid tone, that's the throttle on position. Similarly, that tone turns off at the throttle release spot. So it's a really nice tool for giving the driver the feedback they need for the test being run. In addition, all of the checks built into the software that say, was the run done correctly? Was the kickdown point correct? Did the wind gust too high? Did the throttle off position go at the right location? All those things that go into a good test can be seen in a quick summary report every time the vehicle goes by in the track. So after every pass, typically we're running in both directions. They go down, do a U-turn. They maybe pause briefly, the screen comes up. If it's just green and green, like shown in the middle, they probably say, yep, I'm good, I'm running this test right. They don't even come to a complete stop. They begin rolling, the system's already armed. They go back through and do the next pass. If they failed something, like in the lower right here, in this case, the kickdown for throttle on was supposed to be at -10 with a tolerance of ±1 meter. The actual kickdown was -11.2, so we went wide open too early. So that check failed, and we marked that run as being bad or failed run, and it's automatically excluded from the average that comes in the data sorting and processing later on. And with that, then he's got feedback, okay, I'm a little early on my wide open throttle. I need to adapt the way that I'm actually driving the vehicle in that case. So it's a really nice tool for giving that immediate feedback on, was the test run correctly? Am I running the right standard? And whether it's the person in the vehicle changing the test lab software in the laptop or somebody trackside, again, this driver's aid automatically updates and just shows that information automatically. So you can switch which test type you're running, the displays and values update, and the driver gets the feedback they need to go run a good test. So I've mentioned a couple times about the test lab software and those settings that get transferred like to that driver's aid and the settings that are used to validate, was that a good test, was it run correctly, etc. I wanted to actually show that a little bit in software. I'm not hooked up live to a front end, but I can show these settings, give you an idea of what that looks like. For that, I think I will just switch over to this other screen. I think that should come forward there. So the SimCenter Test Lab software, if you're already a customer that uses SimCenter Test Lab for any kind of testing, it'll look the same in that you've got a documentation tab, there's a channel setup tab, there's acquisition setup, measurement, all those things you would see whether you're doing signature testing or modal analysis, whatever it might be. The thing that's special and different in PassBy are the parameters tab down at the bottom, and then the validation tab towards the end. That I really can't show today because I'm not reading and taking live runs that I can show the sorting, but we could do that as a follow-up for anybody if they want it. But in the channel setup, PassBy is pretty straightforward. And then I've got a couple TACO channels, one for engine speed, one for vehicle speed. I've got two just DC channels. One is kick down for the pedal. So we normally just use a small fiber optic sensor with a piece of tape we put in the back of the pedal. That works really well as far as an analog setup. Like I mentioned, that could be done via CAN bus where you've got to get to 100% throttle. The light barriers are a DC signal. You'll notice though, even though we have two light barriers, one at the beginning, one at the end of the track, there's still only one channel. And I'll show in a second why that is, because they get summed into one single DC input channel for us. And then my two microphones. Now, the other thing to notice here is that these are simply called mic 1 and mic 2. I don't have like a left or a right. Also a very good reason for that I'll highlight in just a moment. If I was using, like this is showing like if I had a wired microphone for the ICP, if it was the wireless microphones, I'd have a choice here for SP-Diff where we use the telemetry and we decode that on a VS8 module inside my SCADAS mobile front end. Things I just thought I'd show that you have to set up as normal channel setup. But if we look at some specific PassBy information, this is what is probably new to somebody, even if they've run SimCenter Test Lab, but never PassBy acquisition. Right away, you'll notice this is showing a specific test. In this case, it's a standard ISO 362 from PAST. It gives me like, okay, what's the microphone position that I need to have? What's the distance to the center line, the driving conditions, the measurement, the averaging, all of that summarized on this table. I'll come back to this in a moment though, because I wanted to show a little bit of the behind the scenes setup that really is done one time, but also relates back to what we're looking at in that channel table. So if I look at the track layout, now normally this is something you set one time for your track, but maybe you've got a portable system, you go to different tracks, or you've got a summer and a winter track, you might have to adapt this and save it into 2 different templates you use, something like that, totally possible. But you can see that essentially it's saying, okay, give me a direction 1 and a direction 2, and then that defines left and right microphone. And if I look over here at the bottom right, you can see it, all I'm really doing is picking which microphone is left or right when I'm in direction number 1. And then we automatically switch those and label them left or right and left, depending on the direction the vehicle is going. The way that we know the direction the vehicle is going is from our light barriers. So I picked that light barrier DC channel that I mentioned, but I've got a setting here for, we use a different pulse level depending on if it's light barrier 1 or 2. So again, based on the direction number 1 and my 2 light barriers, I tell it, okay, I get the higher voltage for light barrier entrance and the lower at exit in direction number 1. So then when it sees a test where I get the lower voltage first and the higher voltage second, it knows that I was running in direction number 2, shown in the diagram up here. So once I've done that, we automatically do the direction detection. We flipped around the left-right microphone indication, and then whenever you're looking at the data later on, you can overlay all your left microphones and it stays with the left side of the vehicle as you would expect. So I think it's pretty obvious, but a really important thing you want to have when you're doing the analysis. And it gives you the efficiency, of course, of running in both directions. We've had some customers that are used to driving in one big loop, which is possible with our system, but with the direction detection, you can go back and forth. And most customers have like a turnaround in their track where they would do that. The other things you'll notice in this setup here are things like, am I measuring RPM? I can say, yep, I've got an engine speed tacho input, number of pulses per rev, whatever that would be. I can define that in the tacho setup. Speed parameters for whether it's radar or GPS or some other pulse train you want to give us. I mentioned like, here's the pulses per meter value. We also even have a speed device delay programmable value. That's because things like the V-Box has, even though it's running at 100 Hertz converting the velocity to that pulse train, there's a known fixed latency that we can account for in the data and actually shift that small amount. And then at the top are things like, where is the computer located? Is it trackside or vehicle? Where is the speed device? Is that radar ground-based, or is that in the vehicle with GPS, etc.? And then which type of telemetry are you using one of ours, etc. So all the normal things as far as the track setup, and at the top I skipped over, distance to the center line, distance tolerance, all those kinds of things. Now, like I mentioned, normally this is going to be set at one time and then you never come back to it because you're using the same kind of track over and over. You're just changing the standard you're running. But if you need to vary any of the values here, now you can see that some of them actually are grayed out. I can't edit those and I try to click in here. That's because this standard that I've selected is locked. So it's the default one we deliver, and you've got the ability to say, I don't want my users to change the default standards. But if you want to modify the standard, you can use the unlock standard button, and then I could edit things like, maybe I want to run this test and there's upcoming regulation and it's simple, they're moving microphones from 7.5 to 10 meters or something. You just put that into the standard itself. So this unlock standard then lets me save it as a new standard that I can then pick from the list, give a different name. We've had customers use this also in the past. If there's something new coming out, or maybe a very small market standard that we had not yet implemented in the software, they have the ability usually to come and build that standard by taking one that's close, unlocking it, modifying the way the test is run, and then saving it as a new standard that they can then use in their testing, until we would then come back and have that available in the standard software. Now that's also worth a quick comment. I mean, we stay very well abreast of all the latest standards, but of course, it's not instantaneous. Many times we do have warning that something's coming, like the ISO 362 took many years, it was in draft and that varied. We even had those draft standards implemented in the software before they were finalized, because our customer said, hey, I need to start using that test, even if that's not the final version, because I have to know if my cars are too loud or not. It was a new test, right? The power to mass ratio style 362 test that was required. So important that you've got that ability to lock and unlock. There's also a vehicle parameters tab up here. Now this is one where customers may interact with this much more often. In fact, I'd argue they probably do have to, based on the actual vehicle being tested in that day. Now, if we look at this, even the data here is going to change based on the standard selected. But there are some things calculated for me automatically. So for instance, if I come into this test for a 362 and I say, oh no, my max rated engine speed in this vehicle is 4,500 RPM. If we watch the values over on the right, when I make that change, it says, oh, okay, then based on your gear ratios and other information you've entered, the target approach speed is now 36 kilometers per hour, 35.9, with a target approach RPM of 33.75. So these are done automatically. You've got the option, am I using the transmission parameters or not? Or do I just want to override this and type in a number? I can unlock it and put that in there for some reason that way. But if I go pick a different standard, like let's say the newer ISO, like here's a light vehicle. You'll see that I'll get a few different parameters, like the curb mass over here. And now that test may be affected by not only engine speed down here, but like the mass of the vehicle. So if I make that 2,500, that can make a change potentially. Oh, you know, I'm actually meant to get the, sorry, I'm driving this from a distance. There you go. I knew I'd get there eventually. So this is the one I meant to show. So now, because I've got information like the mass, the power to mass ratio. So here, when I change the mass of the vehicle, that will change my approach speeds and estimated acceleration values. But you get the idea that the data I put in for the track and the vehicle combined with the standard itself changes the data that both I'm targeting, as well as what gets sent to that driver's aid on the tablet, and the data stored and the averaging method used and all those different things. If we talk about other standards here as well, you can see it's quite a large list, and a number of the newer standards, like say minimum noise, are included in here. So I've got tests for like the ECE 138 regulations for standard and frequency shift. There's other noise tests in here for the different noise standards used in the US. We also have a tool that's available in the software as well. If you're aware of the minimum noise test standards in the US, there actually is an FMVSS tool you have to use from the Federal Motor Vehicle Group to compute your actual minimum noise values. And so we have the set of templates set up to acquire the data, and then you export it in a specific format, and we have a tool to do that. And once you've done that export, then it imports into the FMVSS tool directly and does the processing for you. That's the way, in that case, we do the reporting, because you have to use their tool to actually do that report itself. That's also implemented in as a standalone export executable as part of the software. I did skip over, I didn't talk about really, there is an advanced parameters. This gets quite busy, but it's things like tolerances. What's the position tolerance you want to use? Normally this is written into the standard, but you could decide to be tighter or looser with that based on your needs if you're doing development tests or regulatory testing. Lots of information on how the actual averaging is done. Are you allowing the 1 dB over or under based on how some of the standards are stated? There's some reporting defaults down here, the defaults you want to use for, we have like Word document report templates that can be user edited and changed for logos and content. So all those kinds of things as well. So then really this main standard screen is honestly what you would interact for the most part, because track layout is probably fixed. You may go in and change vehicle parameters. It is possible for those of you who are, I'll say maybe high-end test lab users, you can actually link vehicle parameters to information that you put in on the documentation tab. So it's possible to set up your templates such that you define maybe the vehicle mass here. I showed editing that mass. And that can automatically, when you set it here, transfer into every one of the standards that you pick, so that you don't have to come into the vehicle parameters tab and change it manually. So there's a way to link those test lab documentation parameters to the actual test parameters that are used to calculate all the values for a good pass-by test. So then really it's just a matter of showing a couple things. Like if I pick, here's like a motorcycle standard, F76, you can see this adapts. It's got a lot more text in here because it's different in the way that you're determining the engine speed and the position on the track, where you have to do throttle off. If I look at anything, like here's an ISO test for stop conditions. Different ones in there. There's the regulation 138 I point out, the frequency shift test that you have to do for some of the minimum noise standards. But good. Taking a quick peek here at the questions to see if we had them come in. Do we need standardized road surface to measure? Yeah, it's actually a very good point. So my understanding is that most of the regulations can require a specific road surface, and there's a very specific test that has to be done to verify that the porosity and the sound absorption reflection is within a certain specification. It depends though on which standard you're actually running your vehicle to. I know that some of our customers have gone through a lot of effort to actually have, I've even known sites that had to have the road repaved 2 or 3 times to get the correct values per se for that test. But again, that depends on which standard you're running and whether or not they have in that standard a requirement for a specific road surface. The other reason I know that's important, we've had customers that have had to come back and like clean their asphalt after a certain amount of time because the pores got filled with dust from like a nearby farm field or something like that. And so then that changed the characteristics as well. So that can be an important factor, the road surface itself, but it varies by which standard you need to run. So good question. Thank you. Let's see. Oh, I was going to show one last thing just to actually point it out then, showing concept, the way the validation tab works. So when I've run multiple tests or multiple passes, I should say, of the vehicle back and forth for a given test that I'm doing, I'll get a table that's built up in the upper left that shows which ones were automatically valid based on the checks, and then which ones that were flagged as invalid because some check was failed. Turning those on and off even manually will automatically update graphs on the left. There's everything from the numbers tab, there's graphs that show like the overall levels, positions, things that you'd expect for the pass-by testing. If you had checks that were required, this would say, did you meet them or not? So every individual run you picked over on the left would then show whether or not that run had valid checks or which ones may have failed, octave plots, etc. Ultimately, once you've sorted these runs and made sure that the ones that you want to keep look good, you can overlay them all, make sure they're consistent, that you don't have a very wide gap and variation in them, then you can actually do the quote unquote reporting, where then you'll actually get the numbers themselves. If I switch back for a second to the actual presentation, this has got a graphic that kind of shows that a little bit better. If I just zoom in here for a second. So this is an example of what I was just talking about, where I've got a set of runs on the upper left. You can see that the second and last one were invalid. They failed some check of some kind. But I have 4 valid runs, and for this standard, that was enough to actually processing. In this octaves plot then, it's showing the one run that's highlighted. If it's a 2-gear test, sometimes there'll be multiple tabs down in the bottom section where you can look at the different gears that were running, what the values were there. And then ultimately, there's a little pull down to pick the report you want, and then you click the button like where it says ASAP ISO 362 light vehicle standard, and it dumps that out to a Word document report. Nice and quick for looking at all the data, figuring out what's important, and sometimes you'll get valid runs that look like they have something very wrong with them, and it could be maybe a plane flew overhead or a bird made noise. You never know always, right? I always appreciate the ability to overlay all the runs very quickly and see if I've got one that's very different than the others, and then I'd say, like, well, I'm going to throw that one out of the average because it really doesn't make sense. It doesn't follow the trend of all the other ones. Nice tool for doing that sorting. Lastly, let's talk a little bit about some advanced pass-by noise analysis and predictive work, things that we've done both in software and in our engineering services team. First of all, I'll make you aware that we do have, if you think of it as the exact same test lab software, but for an indoor pass-by test. Now, this does require the right facility, like we can see in this picture in the upper left. This is a very large hemianechoic chamber, and not just because that has a truck in it. You need at least, I would argue, 5 meters of space from the center line of the vehicle to the microphone tips. And I say that because we've had customers that were building indoor pass-by facilities, and they found that even though we can actually adjust in the software to predict from the 5 meter measurement to what it would be at 7.5 meters, and that can be done quite accurately in software, getting much closer than that accuracy goes down. And there were customers that found having the microphones too close to the wall, to the wedge tips, also had a big negative effect when they were comparing indoor to outdoor data. So generally the rule of thumb is you need at least a meter of space behind the microphones, in addition to, I'd say, the bare minimum of 5 from the vehicle center line to the microphones themselves. So you're already in like a wedge tip width interior of the test cells in the 12 to 15 meter range, which is very large, of course, right? I've even seen test cells that are approaching 20 meters across. Similarly, end to end, not as big a deal, but you'll also see that the microphones are spaced like every half meter or 1 meter in this test cell. And what we do is take all those microphones simultaneously and then stitch together based on the speed and computed position of the vehicle on the chassis dynamometer. We stitch the time data together from the microphones and come up with a composite overall level curve. We've got really good information and background that shows that this can be done quite accurately and will compare very well to outdoor pass-by testing, with the possible exception of tire noise. That's the one thing that can actually be quite difficult in indoor pass-by testing, is that the interaction of the tire with the roll for pretty much all vehicles other than motorcycles is generally quite different. So we do have some correction algorithms to actually help with that, where you can possibly run maybe slick tires indoor and add in tire noise from an outdoor measurement, or some other things that can be done in order to give you more accuracy for tire noise contribution inside a test cell. But you'll even see down here that essentially the look and feel of the interior pass-by noise software is really the same, but in this case, I'm defining like an array of microphones, telling it what the signal is from the dyno to get speed, engine speed, all those kinds of things you'd expect. Overall, it's essentially the same process and very straightforward, and can be run very quickly and very repeatably if you have one of these large indoor Hemi-Koch test cells. In addition, we've got some techniques and technologies that help determine contribution of sources. But in the past, when I did this on motorcycles, we just used masking, right? We had our giant muffler we would put on, a giant intake box we would put on. We'd wrap the engine, the mechanical engine of the motorcycle. It was fairly easy to cover it with sound absorbing material. And then we'd essentially make it as quiet as possible. Then we'd remove like an engine cover and then an intake and then the big muffler. And from those changes, we then compute the contribution of intake versus exhaust versus mechanical noise. The automotive people are very familiar with that, doing that as well, I think, in the past with big mufflers, intakes, etc. But that can be time consuming and not all that accurate sometimes. So we have a number of techniques to actually get contribution from systems without having to actually do the masking. And we do that through some airborne source quantification, or ASQ methods, where I can actually measure near field transfer functions, like with acoustic sources. In fact, I think there was one, go back, there's a decent picture here. You know, this is showing like putting microphones around a tire, and then we can put a source at a known location and essentially compute a large set of noise transfer functions from the main contributors: tires, intake nozzles, exhaust outlets, potentially like patches on a transmission or big areas of a transmission, like on a heavy duty truck, whatever we know the major contributors are, get the transfer functions for those, and then compute the contribution individually from the actual real test that was run. And then by adding those back together, we can see how close we get to predicting the real level that was measured in the outdoor test or the indoor test. So it's some interesting ASQ and TPA style techniques we have for doing pass-by noise engineering and really understanding the contribution. And if we take that one step further, we can also have some innovative things we've been doing to try to expand on that, where when I know these noise transfer functions and the contribution of different sources, you could then potentially start quantifying components, intakes, mufflers, maybe transmission energies on a bench test, and then take the component with high-level vehicle information you had measured or broken down from previous tests and put that back together to synthesize a potential pass-by noise result on a vehicle that doesn't exist today by putting together those different pieces of information you have. So this is something that this is not like a push button in test lab where you say, hey, predict my pass-by noise level and we spit out a number. This is more of a research, high technology thing that kind of, it goes from this pass-by noise engineering, which is something we can deliver today in a project sense, and taking that like to the next logical step. And we're working with some lead customers on doing this type of work to actually synthesize or predict pass-by noise levels based on breaking down transfer functions, measured values, even predicted information, maybe from a sound simulation, etc. So really, to kind of summarize, if we wrap up the different slides that I've gone through, we really do think it's a one-stop shop for any pass-by needs. I mean, we have customers that use the system today for just day in, day out regulatory testing. They're very confident they're getting good answers, that it meets the certifications for any ISO or US standard, et cetera. The standards are built into the software. They can tweak if need be, save their own versions. They literally pick it from that pull-down list that I showed you. They tell the driver to go. The driver sees the new information on the driver's aid, and they start going back and forth. So they're doing tens and hundreds of runs in a day to get lots of different testing done at any given test track. But the same exact hardware that we're using for regulatory testing can very easily be used for real, I'd say, pass-by engineering, where you're adding other channels, need to measure some other information. Maybe you have to plug into the CAN bus to get some vehicle parameters, something like that. Because we can do the vehicle-based system with the wireless microphones, putting that front end in the vehicle, even if the driver isn't the one running the test, like I said, that still allows us to get those extra channels and information to help you make engineering decisions for your pass-by noise engineering. That wraps up the slides I wanted to cover. If you think of any other comments or questions, feel free to drop something in there or follow up with us after the fact. With that, thank you very much.